All right, you're an engineer. Your task is to design this system which tows skateboarders up a steep paved hill. We have this electric motor that has computational intelligence embedded in it, and it pulls this rope and the skater up a hill, right? So the way it works is as follows. To begin, the user or the rider grabs onto the rope, points her skateboard up the hill, and then steps onto the board. For a few moments, the skater remains stationary. That means not moving, right? Stationary. The only thing preventing the skater from rolling down the hill is that tension in the rope. During this brief time that the skater is not moving, again, not moving, that smart motor senses the tension in that rope. I'm calling that tension T0. And during that time, the onboard computer performs some calculations, okay? And then the rider hears a brief countdown, 3, 2, 1, 0. So at time t equals 0, the motor begins pulling the skateboarder up the hill. As it pulls the skater up the hill, it increases that tension in the rope gradually, right? So the tension you'll see right here. At time t equals 0, just as it's starting, the tension is equal to T0. The tension is that tension that holds the rider in place stationary, right? K is some positive constant. So as time marches forward, the tension in the rope increases, right? So this gives the rider, doesn't sort of yank the rider up the hill. It sort of gradually increases that tension to make the comfortable ride up the hill, right? So if K is a big number, that tension is going to increase rapidly, right? And K is a small number, that the tension is going to increase more slowly, right? So what we want to do as engineers is choose a value of K, so that after traveling a distance L, the rider experiences a total tension of 3 times the initial tension, right? T0 is the amount of tension that held the rider in place, right? And at that instant, when it reaches that distance L, the tension will be adjusted again so that the rider travels uphill at a constant speed. So there's how we are designing this tow system, right? With those goals in mind. You as the engineer, I'm going to have you calculate a few things to figure out exactly how this thing is going to work. All right, so following the problem-solving checklist, first thing I'm going to do is draw a picture of the problem. On this picture, I'm going to label some particularly important things as I solve the problem. So one thing I have here is the angle of the road. I'm also going to define this variable s, which is the distance the skater has traveled from its original starting location. And finally, I'm going to define some basis vectors that I'll call e hat 1 and e hat 2. These vectors are defined tangent and perpendicular, respectively, relative to the slope that the skater is being towed up. Now, with these defined, I can write the position, velocity, and acceleration of the rider as s in the e hat 1 direction, s dot in the e hat 1 direction, and s double dot in the e hat 1 direction, respectively. Now, in this first question of the problem, we are asked to find the initial tension in terms of the skater mass, including that skateboard, the gravitational field strength G, and the roadway angle theta. So following the problem-solving checklist, we list our givens, m, g, and theta, as well as the quantity that we are asked to find, which is that initial tension T0. Then the next thing I do is draw a free body diagram. In this case, my free body diagram is going to be the skater and her skateboard, right? Both objects move together as one. So this rectangle here will represent the skater and the skateboard. Here I have the weight of the skater pulling down. I have a normal force from the ground that prevents the skater from penetrating through the ground. And I have the tension force from the rope, right? This tension force from the rope is preventing the skater from rolling down the hill, right? This is holding the rider in place. And that's it. There is no friction force in this problem. We were told explicitly in the problem, somewhere in there, that there's no friction. So let's leave the friction out. So here we have our free body diagram of the skater. And since I'm anticipating putting these in equations, let me just write these forces a little bit differently. So that normal force is all in the E hat 2 direction, right? So that's all perpendicular to the road. And similarly, this tension is tangent to the road. So let me just call this T in the E hat 1 direction. The weight has components in the both in the E hat 1 direction and E hat 2 direction. So why don't we take this opportunity to decompose that into components? And also I'll write it in terms of quantities that are given, right? I'm given the mass and I'm given the gravitational field strength G. So I'll write this as mg. In the E hat 1 direction, this should be minus sine theta. And in the E hat 2 direction, I should have mg minus cosine theta, like so. Now the next thing we're supposed to do is draw the mass acceleration diagram. That's the next step in our problem solving checklist, right? As we do, let's think about this, and actually let's go back to the problem statement itself, right? We're supposed to find T0, the initial tension in the rope. What's T0? The T0 is the tension we have in the rope when the skater is not moving, right? When the skater is stationary, right? That's what the problem says. Okay, so going back to our work over here. So now here we'll make the tension T0, not just any T, but T0, when the rider is stationary, when the rider is just sitting there for some amount of time. If the rider is just sitting there, then mass times acceleration is what? It's just a big fat zero, right? It's zero. There's no movement, there's no velocity. Velocity is zero for a while, so therefore acceleration is also zero for a while. This first part is a statics problem. So when I set up Newton's second law here, and I sum up all my forces set equal to mass times acceleration, if mass times acceleration is zero, then all these forces have to balance each other out. They have to add up to zero. And remember where we're going with this. What we want is this initial tension, the T0. The tension T0 is all in the E hat 1 direction. So if I look at Newton's second law and just look at the E hat 1 component, right? So we're just going to add up all these forces, has to equal zero. But if I just look at the E hat 1 component where this tension, what I want, I get T0 in the E hat 1 direction. Again, I'm just reading off my diagram. For my weight, I've got minus mg sine theta. The normal force is does not have a piece in the E hat 1 direction, so that's all I get on the left-hand side. This has to equal zero. Aha! Now we're getting someplace. Let me just scroll up real quick so I have some room. So what does this tell me? I can solve now, right? So this tells me that T0 is mg sine theta. So looky here, what do I have? I got T0, my initial tension, that's what I want to find in terms of m and g and theta, and those are the quantities that are given to me. So it looks to me like we're finished with question number 1. Of course, before we take this as our final answer, we should do a dimension check. So on the right-hand side, we've got a mass. G has units of length over time squared, and mass times length over time squared is a force, which is exactly what we want. And by the way, sine theta, right? Sine of theta would be if I were to draw a triangle over here, like so, sine of theta would be the opposite side of this triangle divided by the hypotenuse. So it's a length divided by length, so sine theta itself is unitless. So there we go, got a force. And question number 1 is finished. All right, so let's move on to question number 2. It says, what are the dimensions of the constant k in equation number 1? Right, let's go back here, look at equation number 1. So this is the expression for the tension, right? So the tension was the initial tension T0 plus some constant k times time. What are the dimensions of that k? And just so we're clear, I'm looking for dimensions that contain just a mass, a length, and or a time. So I've written that expression right over here. And let's just go through it piece by piece. This t on the left-hand side, that's a tension, right? So tension, of course, is mass times length over a time squared, right? And then we just found out in the first problem, this T0 is also a tension, right? It's a force. It's a mass length over a time squared, right? So I've got on the left-hand side, mass length over time squared. The right-hand side has to be mass length over time squared. This first term is mass length over time squared. And I have to add to it something else. And whatever this thing is right here, it should be a mass length over a time squared. The expression does not make sense unless these units sort of work out. You can't add things together that are of different dimensions, right? Now we know that the time here is a time. This thing is time, right? So in order for k times time to have dimensions of mass length over time squared, k must have dimensions of mass length over time cubed, right? Has to be mass length over time cubed times a time, which would give us a mass length over time squared. So there's my answer to question number 2. All right, so let's go back to our problem. Question number 3 asks, find a mathematical expression for K in terms of that initial tension G, theta, and L. All right, so according to the problem-solving checklist, we list these things out, right? We're finding K in terms of the initial tension G, theta, and L. Now, it's important to note, as was stated in the problem, we are not given mass this time, right? Not given mass, but we've already found mass in terms of these quantities, so that shouldn't be a problem for us. So now in this part of the problem, the free body diagram is exactly the same as it was before, right? But instead of the tension being a constant value, it's going to be increasing gradually in time. And because that tension is increasing, the body is no longer in equilibrium, and we're going to get an acceleration. So let's redraw the mass acceleration diagram. But this time the acceleration will be not 0. So I'll write ms double dot in the e hat 1 direction, right? At the very beginning we said that the acceleration was s double dot e hat 1. So let me write it that way. So now when I write Newton's second law and check out what it looks like in the e hat 1 direction, right? E hat 1 is where I have my acceleration. What do I get? Again, reading directly off the free body diagram, I get the tension force. So let me put that in there. So here's the tension. And then I get the weight. So in the e hat 1 direction, I get minus mg sine theta. And this has to equal mass times acceleration, which is all in the e hat 1 direction. So I got ms double dot. Now I can do the same thing in the e hat 2 direction as well, right? That would give me an n and a component of the weight mg cosine theta minus mg cosine theta, and no acceleration. But this would just allow me to determine the normal force. And in this problem, I don't care what the normal force is because there's no friction. So I'm just going to leave that out. So let's just go with what we have in the e hat 1 direction. I'll make a little more space here. All right, so now what I'm going to do is let's recall what the tension was, right? Now the tension is changing in time, right? So let me write that expression here. So if the tension is now the initial tension plus k times t. Cool, so that's the t. Let's include the minus mg sine theta, which is the piece of the weight. And this is equal to our acceleration. Now what I want you to do is recall our previous result, right? This T0, that's just the initial tension. That's the tension that we had when the skater was stationary, wasn't moving at all. And you recall, I don't have it here, but you recall we found this initial tension was what? It was m times g times sine theta. Now check this out. So I got mg sine theta plus kt minus mg sine theta. So this is rather convenient, right? These two mg sine thetas cancel each other out. So this tells us that ms double dot is equal to kt Or I can say that the acceleration, s double dot, is equal to, let's say, k over m times t. So now I have an expression for the acceleration, right? In these types of problems, I've always been looking for expressions of acceleration. Here we are in this problem, we've got one. Unlike some of the example problems we've already done, this time the acceleration is not constant. It's changing in time, right? But other than that, the problem is essentially the same as the other problems we've already seen. I'm going to suggest we draw a few plots. Let's make some room for them. So therefore, this expression we derived for the acceleration, if I were to put it on my plots, this would be a linear function of time. Now to find the velocity, right, this is the s dot, all I need to do is integrate the acceleration over time. Right, I'm integrating this linear function. When I integrate a linear function t, I get 1/2 t squared, right? So that's why we have a 2 in the denominator there, and t squared right here. And of course, we get a constant of integration. I'll call it c1. Now to determine the c1, the constant of integration, we apply the initial condition. The relevant initial condition for this problem is what's the skater doing at time equals 0, right? At time equals 0, the rope is just starting to pull. At time equals 0, she's still stationary. So therefore, s dot at time 0 should be 0. So if I take this expression for s dot here and substitute time equals 0 in there, I get 0 squared times k over 2m plus c1. And of course, this 0 squared just annihilates this entire term, leaving just c1 must be 0. Therefore, we find out that the expression for s dot, or our velocity, is just k over 2m times time squared. And if I were to plot that, what would it look like? Over here, s dot starts at 0, and it's a parabola, right? It starts off with 0 slope because s double dot is 0, and this thing should grow quadratically. I'm trying to draw this thing more or less like that. Now before we go any farther, I want to sort of remind us what we're doing. It's easy just to get sort of in a sort of automatic loop of calculating an acceleration, then integrating to get velocity, and integrating again to get position. But let's think about where this is going, right? What are we trying to do here? Let me go back up to my givens. This is why we write out the givens and the finds. So we're given, let's suppose, we're given the initial tension in the cable to hold the skater at equilibrium, a g and theta, the slope, and the length, or, what's this length again? We'll have to go remember. But the objective is to find the k. K was the rate at which the tension was increasing. And the onboard computer here on this skater towing system is computing a k so that the rope experiences a tension of 3 times t0, 3 times the initial tension, just as the skater reaches a distance L from her starting point. It's the one that gives you this exact tension after traveling this distance, right? So we're going to need a distance. So this is telling us that we are going to need to integrate one more time so that we can take the velocity expression we have right now and obtain position as a function of time. So we find that position s is the integral of k over 2m times time squared. Again, we're integrating with respect to time. What does this equal? The integral of time squared is 1/3 time cubed. So my constant now becomes k over 6m, right? I'm going to bring another 3 into the denominator, times time cubed. And then we have to add in our constant of integration. I'm going to call it c2. Once again, we have to satisfy an initial condition. So what's the initial condition? At time equals 0, the skater's at the bottom of the hill, which we called s equals 0. So s at time 0 has to be equal to 0. So I take my expression, k over 6m times t cubed plus a constant of integration. What I need to do is take that t cubed and put in a 0, right? So let's take that t and put a 0 in here, so it's going to be 0 cubed. Doing so gets rid of this entire term right there, just leaving c2, which has to be 0. And therefore the position s has to be right up here, k over 6m times t cubed. Nice. Look how clean that is. Kind of like that. And now if I were to plot the position, it's an increasing function, right? It starts off at s equals 0, and it starts off even flatter than s dot, right? Because a cubic is flatter than a quadratic for low values of s, and then it skyrockets up kind of like this. There's my function for position. Now here's my position. Now I'm interested in what happens when the position reaches some value of L. I'll denote that location L right there. Well, I've got this expression right here. What I can do is I can find the time at which the position is equal to L. Draw a little construction here. So here's L, and the place where this yellow curve crosses the red curve, maybe I'll indicate it like so, bring it down, and what we have is a time, TL, the time at which the skater reaches a distance L from her starting point. Mathematically, what we're doing is we're saying S evaluated at time TL is equal to k over 6m TL cubed. So time TL is what happens when the position is equal to L. Pushing terms around a little bit, I can say TL cubed is equal to 6ml over k, which would mean that TL, this time here at which the position is equal to L, is going to be equal to 6ml over k to the power 1/3. Now, why is this important? Remember, tension is a value that's changing in time. So tension is just T0 plus k times t. But if we want to know the tension at time TL, what I need to do is just substitute my value of TL in there. And what I get is T0 plus k times 6ml over k. Remember, I have to multiply or take this all to the 1/3 power, right? I'm just putting TL in there. So here's the tension as the skater is crossing that magical distance L, right? When the skater crosses that magical distance L, this has to be 3 times the initial tension. Ho ho ho. Now what can I do? So I should be looking at this expression right there. What I can do is I can bring this tension over to the other side. Let me just write an equality right there. Bring this tension over to the side, so on the right-hand side I would have 2 tensions, or 2 initial tensions, T0. On the left-hand side, I'm going to keep this k. So I have a k to the power 1, or k to the power 3/3, divided by k to the power 1/3. So that would leave a k to the power 2/3, all times, was it 6ml to the power 1/3, right? And now I can solve for k to the power 2/3. Aha! Now we've got k to the power 2/3, and it turns out this other quantity has an m in here, and I'm not given m. That was not one of my givens. But I did have this nice little result from question number 1. Remember question number 1, I found that the initial tension was mg sine theta, which means that m is equal to T0 over g sine theta. And what I can do is I can take this m and put it into there. And then what? And then you can manipulate things for a little while. It takes a few lines. But in the end, you get this really cool expression. I got 4g sine theta over 3l, and then I'm going to take the square root of that thing and multiply it by T0. And I claim that's my answer. I feel pretty confident about it because I checked my results a couple times, 2 or 3 times, everything seems to work out, but let me run a dimension check at least. That might catch some sort of error. This value of K, remember what we're expecting for that? This is a force per unit time, so it's a mass length over time cubed, right? So this alphabet soup of symbols over here better be mass length over time cubed. Let's try it out. So inside the square root sign here, I got 4 times g times sine theta. Right? Sine theta is just a length over length. We've already discussed that. 4 is just a number. So what we have inside that, inside the square root, in the numerator, we have a g, which is a length per time squared. And then I'm dividing by 3 times the length. So I'm dividing by a length, right? And I've got some dimensionless stuff in there too, but that doesn't add anything to it. So I take the square root of that, and then I multiply by T0. T0 is a force, so that's a mass length over time squared. Now let's look inside the square root again. Actually, let me put an equal sign there. Inside the square root, what do we find? We find that this length and this length cancel each other out. So inside the square root, I have a 1 over t squared. Yeah. And on the outside, I've got mass length over time squared. The square root of 1 over t squared is just a 1 over t. So this just is a mass length over t cubed. And that's exactly what I was hoping for. So therefore, my dimension check is working out. And I'm starting to feel a little more confidence in this. I'll say even more confidence in this solution right here. So I am going to put a box around it and say, I've answered the question. Now in the fourth question, what we're supposed to do is the following. So we're going to continue the analysis to find the tension in the rope just after the rider passes that distance L. So let's go back and see what the problem statement says again. So it says right here in item E, after the skater passes the distance L from the starting location, the smart motor adjusts its tension again so that the rider travels uphill at a constant speed. That's telling you exactly what's happening, right? So after the rider passes the distance L, the tension is no longer 3 times initial tension. It's the tension that results in the rider traveling at a constant speed. Let's go back to our free body diagram. So here is our skater being pulled up the hill. The skater has all these forces acting on her. And then at time L, or just after time L, the skater is moving at constant speed, right? Constant velocity. Again, we're going to apply Newton's second law. Sum up all these forces equals mass times acceleration. But if velocity is constant, then mass times acceleration is 0, right? There is no acceleration. So all the forces should add up to 0. So therefore, if we look at just what's going on in the E hat one direction, I've got the tension minus my component of the weight has to equal 0. So therefore, after passing that distance L, the tension has to equal this component of the weight again, right? Just as it did in, what was it, question number 1. There's our expression for the tension at that time. And since the problem asks us to express that tension in terms of T0, G, L, and theta, the final answer should be tension is equal to T0. And that completes question number 4.